All right, so for 3.1, you're trying to find extrema. Extrema are just maximums and minimums on your graph there. So if you look at this first couple of graphs here, these are all the graphs for y equals sine x, but the difference is the windows that you're looking at. So the first graph, we're looking at this from 0 to 2 pi, which means pi would be here, and this would be pi over 2 and 3 pi over 2. So if I ask you to find the maximums and the minimums, you're probably going to say the max is right here. When x is pi over 2, the height is 1. And that's a minimum when x is 3 pi over 2, the height is negative 1. If you look at the next graph, the next graph only goes from 0 to pi over 4. So this point right here on the end is 0, 0. That's a minimum. And at this end here, if I plug pi over 4 into sine x, I'm going to get about 0.707 or 1 over root 2 if you use an exact value. And that's the highest point on that graph. If you look at the last graph we're looking at from pi to 2 pi. So the maximum values happen at both of these endpoints at pi comma 0 and 2 pi comma 0. So this particular piece of the graph has two maximums, and it has one min right here at 3 pi over 2 comma negative 1. So the max and the min is going to depend on how much of the graph you're looking at. So all of these intervals have different maximums and minimums depending on how much of the graph or how little of the graph you're looking at. So these maximums and minimums happen at these things called critical numbers. And the way you find critical numbers is we're going to find the places where the tangent line has a slope of 0. So where do you have a horizontal tangent? It also happens if you have any vertical asymptotes or discontinuity points or sharp points, sharp turns in your graph there. And those are called critical values. Sometimes they're going to be maximums and minimums. Sometimes they may be places where the derivative is undefined, like we said you had a sharp turn or an asymptote or something like that. All right, let's slide this up here. All right, so to find a critical value, we figure out where is the derivative 0 or where is the derivative undefined. So where is the derivative equal to 0 or where is it undefined? So if you look at the first function here, this is a nice cubic graph. This is the sketch of the graph. If I find the derivative, I get 3x squared minus 6x. And to find the critical values, I would set the derivative equal to 0. And I get 3x times x minus 2. So 3x is 0. So x would be 0. Or x minus 2 is 0, which means x would be 2. So both of these are called critical values. And if you look at your graph, what's happening at those two particular x values when x is 0, that gave me a maximum on the graph. It's a high point on the graph. And if you look at this value where x is 2, I have a minimum. I didn't figure out what the y value was, but we can see that that's going to be the high point and the low point. That's the x value where that happens. All right, so let's do something with these now. Let's come up with those maximums and minimums. So now if I'm looking at a closed interval just means I'm not going to look at the entire graph, I'm just going to look at a little piece of it. So for this first example here, you're looking at this parabola x squared minus 2x plus 4, plus 2x minus 4, and I'm only looking from negative 5 to positive 1. So that's the only piece that I'm going to look at on the graph. Now if you look at the graph, it looks like that's the highest point and that's the lowest point. Let's figure out what those values would be. So to find those values for the maximum and the minimum, we're going to find critical numbers, which we just did by taking the derivative, set it equal to 0. We're going to plug back into the original function each of those critical numbers to figure out what the height of the graph is going to be. And then we're also going to plug in the values for the endpoints back into the original function, because if you look at this graph, it looks like this endpoint is the highest point. So the max or the min could happen at the endpoints as well. And then when we look at the outcomes, the smallest value that we get for the outcome is going to be the minimum. The greatest outcome is going to be the maximum. All right, so let's get critical numbers to start. So the derivative would be 2x plus 2. If I set the derivative equal to 0, I get 2x equals negative 2, and then x would be negative 1. So that's a critical value, critical number. If you look at your graph, here's where x is negative 1. You can see that looks like the lowest point on the graph there, and we're going to prove that it actually is. So that's the first step, get the critical values. Second step says to plug that critical value back into the original function, into f, not the derivative. So back in f, I'm going to plug in negative 1. So negative 1 squared plus 2 times negative 1 minus 4. That gives me an outcome of, what do we have, negative 5. So that's my second step. Third step says to plug in the endpoints. Now I'm going to plug in, here's the endpoints for my interval. I want to plug in these values to see if the endpoints are the greatest value. So if I plug negative 5, that's the left endpoint, into my original function there, negative 5 squared, 2 times negative 5 minus 4, that's going to give me a value of 11. If I plug the other endpoint in, which is 1 squared, 2 times 1, minus 4 gives me an outcome of negative 1. And then I want to see which of these is the largest outcome. The largest outcome was 11. So that's going to be my maximum. That's my y-coordinate. When x is negative 5, my height is 11. So that was a max. And then the smallest outcome was up here at negative 5. That point is when x is negative 1, my y value is negative 5. So that's my minimum. And if you look at the graph, that's what it looks like. This is the point, negative 5, 11. Okay, and the other point was negative 1, negative 5, which you said was the minimum. And that's what it looked like. But you're not always going to have the graph, so you can do this using calculus. All right, let's look at the next example. So the next one's a little bit more complicated. If you look at this graph, we have a sharp point on this graph, so we're going to have a place where the derivative is not defined. There's a sharp point right there. So something's happening there. It looks like that might be my minimum. Looks like that sharp point, and down here it looks like these two values might be my maximum. So we're going to go through and prove that those things are indeed what we think they are, or maybe they're not. So let's find the derivative. So the derivative for this is going to be 2. 2/3 times negative 3 is going to give me negative 3x to the negative 1/3 power. Actually, it gives me negative 2. Fix that, sorry. So I got the derivative. Maybe I want to write that this way. 2 minus 2 over x to the positive 1/3. So if you look at that derivative, I have a problem here. When I have this derivative, if x equals 0, I'm going to have 2 divided by 0, which is undefined. So this is a critical number because the derivative is undefined. So I already have one critical number. I still haven't solved my derivative, though, to figure out what else x could be when I set it equal to 0. So I'm going to go back to this and see if there are any other critical values. So I know a place where it's undefined. Let me see if there's any places where it's equal to 0. So I can solve this. I'm going to put the 2x to the 1/3, 2 over x to the 1/3 on the other side. I can cross multiply and divide by 2. I get x to the 1/3 power equals 1. So if I cube both sides, I get x is 1. So there's another critical number. So I have two critical values from where my derivative is 0 and where my derivative is undefined. I also have to plug in the endpoints of my interval. And I'm plugging these back into the original function here. So if I plug in 0, I'm going to have 2 times 0 minus 3 times 0 to the 2/3 power. That's going to give me 0. We'll have 2 times 1, 3 to 1 to the 2/3 power. That's going to give me negative 1. And then I'll have negative 2 minus 3. It's going to give me negative 5. And if I plug in 3, this one doesn't work out nicely. I'm going to have 3 to the 2/3 power. This is going to be a decimal. You can put that in your calculator there. It's going to give me negative 0.24025, so about 0.240, I'm sorry, negative. And then again, if we look at these outcomes here, the biggest outcome is 0. So when x is 0, y is 0, that's going to be my maximum. We said this point over here also looked like a maximum, but if we look at that outcome when x is 3, my outcome is negative 0.240. It's actually just below the x-axis. So it's not quite as high up as this other point is over here. And then my smallest outcome was this negative 5. So when x was negative 1, y was negative 5 was my minimum. Okay? And then the last piece of this, they ask you to decide whether you have a minimum or not. So if you look at this, to have a minimum point, it has to actually be a point on the graph. So if you look at this first one for 57A, this point is the lowest point, so it does have a minimum there. For this one, the lowest point is actually an open circle. There is no point there, so it doesn't have a minimum. It has to be enclosed. Same with 58A. There's no point at that open circle there, so it doesn't have a minimum. This one, that same graph, now the point's enclosed, so it does have a minimum at that particular point there. Slide this up a little bit here. And for 59A, again, there's no point there, so there's no min. This one is kind of the same graph, but now the point's redefined down here. This point's lower than any of those other points, so that is a minimum. This one, the graph goes down, but the lowest point here is an open circle, so I have no minimum value. I can't figure out what the number is there. And the same thing for this last one here. It's still the same kind of decreasing graph, but they redefine this point lower than the graph. So that one will have a minimum. So that was actually the last few problems that you were supposed to have in your homework. We just kind of did them together. And then this one was another homework problem that we kind of just added to the notes. They want you to label all these points as something. And they talk about absolute max and absolute min. That just means there's no other points higher or lower than that one. Relative max, relative min means it's a high or low point. It just may not be the highest or the lowest point. So if you look at this point A, there's no values that go below it, so it's going to be the absolute minimum. No points lower than that on the graph. If you look at B, over here, G's going higher than that, so it's a maximum, but it's a relative maximum. It's special, but it's not the highest point. Point C here goes through the x-axis. It's not a max or a min, it's just a 0 on the graph, a 0 or a root or a solution. Point D is a low point on the graph. It doesn't go as low as A, so it's a relative minimum. Point E goes up. It's a higher point, but it's not the highest point, so again, it's a relative max. It's also a sharp point on the graph, so the derivative's not defined at that point, but it's still a maximum. Point F, it's a 0 for the function, because it crosses the x-axis. It's also a minimum point on the graph, and it's not the lowest, so it's the relative min. And then finally, this point G here, if it was enclosed, if that circle was enclosed, we could call it an absolute maximum. Since it's an open circle, it is nothing. Or they said use the word neither. If it was enclosed, we could call it a maximum or an absolute maximum, but since it's not, we don't know how high it's going to go there. So that's it.